So I basically we predict whether a branch is to be taken or not taken at the fetch stage, correct. So at the fetch stage I give the address of the the particular PC. If that address is actually stored in your branch target buffer, then that is a conditional jump. I have the target address of that conditional jump. Along with this, I also have the prediction data. From the prediction data, if I find out yes, it is going to be taken, then immediately I load this target address. If it is not taken, I just leave it off. It goes to the next address. So by the time I come to the execute stage, that is the point where I realize that the jump is what is going to actually happen to the jump. So far I have predicted. So if my prediction is wrong, I have predicted it will be taken and actually it is not taken, then I go and flush the pipeline. All these three whatever I have fetched, the other instructions and decoded and data fetch, whatever has happened for the others, I have to go and flush it out. Okay, right? Now please note that in the first 3 stages I am not changing the state of any system, any hardware. Fetching data is only reading, decoding the instruction doesn't mean I am changing any register or anything, and so fetching instruction, fetching data also I am only fetching the data, I am not changing anything. So all these 3 stages are read only stages. I read something, I process something, but I am not updating the context of the process. I am not updating any general purpose register, nor am I updating anything. Okay. So what does this imply? My flushing operation is going to be very, very simple. I have to just erase it and put, what do you put there? We put no ops, right? We have already seen what a NOP is, right? I just put a no op there for all the 3 stages and it just progresses. So please note that branch prediction also crucially depends upon the fact that I can afford to make a misprediction and quickly recover from that misprediction. And the reason being that the 3 stages before execute are read only stage. Read only in the sense that I am not going to go and update or change the context of the process. I am not going to update the general purpose register, I am not going to update anything, flag register, etc. Correct? Okay. So this is one point which makes these type of prediction mechanism possible. Okay. Now what is more pending in branch prediction is how do we arrive at the prediction data. Okay. So let us take some trivial prediction strategies. Suppose I say always it is not taken. What will happen? Who will benefit? Always not taken.
There will be no flushing out.
Huh?
There will be no flushing out often, but
no, that flushing out has nothing to do with prediction. If you mispredict, then
yes,
you will flush out.
it's highly probable that this is a misprediction because taken is better than not taken.
Taken is better than not taken. Huh? Think. Always I say not taken, no problem. This is what we call as a static predictor. Who will benefit? How will you even think about an answer? Suppose I ask this in the quiz, no, how will you think of an answer for this? Loops. Yeah, correct. So, very good. Next. Which loop will benefit from always not taken? Huh? Entry. Which entry? Entry control. Entry control is okay. Okay. So, what can you give me an example of an entry control loop? For. Okay. So, if I have a for loop or a while loop, what you do is in the for loop, the way, see, you can translate it in any way, but the correct way of translation would be that I check here. check what for a condition, right? If the condition, so this is checking would be something like a compare instruction, etc. And here I make a decision to jump on end of loop. I will make a decision to jump on end of loop here, and here would be the body of the loop, and your jump actually will jump here. So here there will be an unconditional jump which will take you back to this checking condition. So this is the structure of how a while loop or a for loop. So there will be some condition check to start with, and then a decision to jump. So this will be the conditional jump. Here will be the conditional jump here, correct? And then I have the body of the loop, and then unconditional jump which will again take at the end of this. So this is how a for loop can be translated. One of the ways by which for loop gets translated. For and while loops. Okay. Now what do you see here? The interesting thing. So you have done the translation, right? You have generated code in your previous course in third. So this is how you did it. You remember? Okay. Chal. Now, assuming that the for loop is going to execute for say 10,000 times, in 10,000 times, 9,999 times you are going to have correct prediction, because 9,999 times this jump will not be taken, the body will be executed. There is exactly one time where there is exactly once, that is at the end of loop, where this condition becomes true and I jump out. The remaining 9,999 times I will not be taken. So my prediction is correct for 9999. Suppose I say always taken. That is true when I have something like do while. That is, I want the body of the loop to execute once and then take do while. Okay. So if I do while, what happens? So I will have the body, and I will have a condition check here, and then I will have the conditional jump here, which will basically take back. So for majority of the time, what happens? I will be taking this, the branch will be taking, I will go back to the body, only once I will come back. Do you follow this? So if I have an always taken type of a criteria, then what happens? Then this works. If I take always not taken, then for and while loop works. And these are major part of your program, right? For, while and do are major part. Other than that, there could be some internal if else statement or switch statements, right, which are different. Okay. Now, so I have taken, not taken. So these are basically static prediction, because I don't change the prediction at all. I don't change the prediction at a regular interval. So I just do this, right? I just fix the prediction. So that's why I call it as a static prediction. It is fixed in the architecture, and every time it is not taken or taken. Okay. So now, how will you decide? Suppose you are saying that I don't want to invest so much on branch prediction. I don't want to complicate the hardware. Okay. Now, you are given a mandate to do either static, either not taken or taken as a static prediction, right? Now, how will you decide whether to put not taken, or how will you decide how will you put taken, and how will you interact with the compiler guy? So there is one compiler person, then you are the architect. Now you are given a mandate, you should only do static prediction, correct? So either you have to decide I should put not taken, or I should decide that I have to put taken as a prediction. Now you have to interact with the compiler guy. Now how will you make this decision? How both of them together will sit and make the decision? You got my question? Yes, okay. Give me the answer. For what program?
Compiler can translate it always into either empty or exit.
Correct? So that's the interesting question. So the compiler guy will tell, you decide and tell me. To whom? To the architect. You decide and tell me what you want to do. Okay. So the architect will say, okay, always not taken is preferable. Then the compiler should translate every do while statement to a while do statement. Correct? Or vice versa. I will say always taken. He is very happy with always taken. Then he has to convert every for and while statement to a do while type of concept. So how do you convert a do while to a while? Which is easier? For while, for and while construct to do while construct, or do while construct to for while? Do while. So how do you do it? How will you convert do while to while do? So that initial condition, one code you make up, then put while condition, then body. So this is the transformation that you do. I will move one version of that body, I will put for the first condition that I will put in above, then I will put a while body. So this is how I can convert a do while to a while. But the other way is slightly tricky. Okay. Now there is some other if branch. So what do you get here? So what this is the first thing that we are starting off on, what you call as something more on architecture based optimizations. I have this, so I say I have an ARM architecture, I have an Intel architecture, I have some RISC-V architecture, right? I have the Shakti architecture from IIT Madras. I am writing a compiler, I want to optimize it. What does it mean to optimize something for an architecture, right? This is one example. No, there are umpteen number of examples, but this is one thing that we could start. Now, this is all about static prediction where I fix it for once and I don't change, and that will work for 99% of the case. Now, whatever we are going to talk further is just about 1% of the case, right? In my opinion, we can just throw it off and still it will work. We will not get some big hit there, right? And for every prediction mechanism, I could get a counter example which will kill it, but it will not be the real case, right? So in a normal programming environment, you may not get something that complex. Say I specifically write a program to kill an architecture. That will not happen in practice. Okay. The serious stuff about branch prediction ends here. If the compiler does this and all this do while for loop, so if you take any programming language, you will have these type of constructs, right? So so we can generally characterize as entry check or exit check, right? So if everything is going to be entry check, then I take not taken, it will work. If everything is going to be exit check, if I put taken as the static prediction, it will work. But what beyond this? Okay. Now let us go to something called the dynamic branch prediction. Okay. So what is dynamic branch prediction? I keep changing my prediction for every branch. Let us say in a program I have 1005, 1025, 1040, 1053. So let me say there are branches at these points. So, in your branch target buffer, I will have these entries 1005, 1025, 1040 and 1053. I will have some target address, namely L1, L2, some address to which it can branch, and I will have a prediction bit here. Normally, we assume that initially they are all not taken. Right. Now, since I said prediction bit, this is a 1 bit prediction. One bit prediction. Now, what will happen is, always the prediction bit will be adjusted or will be changed to what happened in the previous instance. Okay. If so, always. So, if in the previous instance, if I am executing 1005, initially it is not taken. If it is going to be not taken, it will be continuing in not taken. But if it becomes taken, then you will go and change this to, this will become taken. So, whatever happened in the previous execution of that branch will be the prediction. So, this is what we call as an 1 bit prediction. Okay. Whatever happened in the previous execution of this branch will be taken as the prediction. So, it can become taken, next time it can become not taken. So, this type of a dynamic branch prediction will be extremely useful when you are having these type of this if statements, okay, if else statements. So, can you give me so for a 1 bit predictor, so how will so can you give me an instance where this will have 100% failure and an instance where it will have 100% success? 100% success is trivial, just get a branch, it will be always if 1 equal to 0 or something like that you can put. So, I can finish it off. But can you give me something where it will have 100% failure? So, initially this branch is not taken. So, this is the prediction and this is the actual action. So, this becomes taken. So, essentially next time when this branch is executed, it will say taken, but actually it should be not taken. Next time when it comes, it will say not taken, but actually it will be taken. Like this. Can you give me a realistic example for this?
Numbers to see if it's divisible by 2.
Exactly. Good. Beautiful. So, if I have a for loop, so a little more practical way of answering. Your answer is absolutely correct, but still you can answer like this. And I go and say if I mod 2 is equal to 0, something I try and do this. Ensure that the code that is generated will take if I mod 2 is 0, will take if this condition is satisfied. Right. Then what will happen? So, I can say I mod 2 is not equal to 0. So, you start with 0. So, it will predict not taken, but actually it will be taken. Next time when I equal to 1, it will be actually, it will predict taken, but this will be not taken, and so on. Okay. So, this is a 1 bit prediction, and this will basically there is an example, there is a trivial example which can kill this 1 bit prediction. Okay. Now, but where will this 1 bit prediction be very useful? Can you give me an example where one, so why I teach 1 bit prediction if it is a stupid thing? Where will it be useful?
Both the loops it can handle both the loops.
Both the loops and compiler. Okay. Both the loops, that is entry check and exit check loops exist, and the compiler does not do any optimization. Okay. So, where will you get, why should the compiler not do such optimization? Today you sell a software, right, it executes for next 5-10 years, correct, and what would have happened, just imagine you assume not taken and you released a software for a nice architecture, and suddenly you start fighting with that architecture fellow, like this company and that company has a huge fight, or somebody else bribed that company to kill you. He has to not do anything. That next time he creates that architecture, you assume not taken, right? I will put taken there, that's all. And if the architecture actually becomes very powerful, I am talking political things here, okay? If the architecture actually becomes very powerful, then your software recedes to, assume the architecture is ARM and you are a simple one app. People care a damn for it, okay? So you are completely gone. You have made a compiled executable, and now you say you have made that with not taken as this, and then finally if you compile that and put here, then the fellow changes the strategy, then you have to go and redo your app and release it again, right? And if it is a commercial app, right, you may not be in a position to immediately redo. So lot of issues come. So if your app is going to run damn slow for say next 1 week, right, people will discard your app and take another app, right? So if I am an architecture company and you are an application and you are trying to dominate over me, so what should I do? I should have a software team which can write a software as good as yours, and then I will go and change some architectural parameter so that your app gets screwed, okay? So enough. So traditionally people will not depend upon an architecture, they will make it architecture independent, right? So if you study the XV6 operating system next time, you will see that none of the features, none of the great features of x86 are used in that Linux, right? For example, segmentation is not used at all. There will be some segment, but it is not used in its full glory, that what we have talked of, right? For example, there will be segments that are merged. For example, code segment, stack segment, everything will start from a same address, and we leave it to the operating system to distinguish between where the code should be and where the stack should be. So I declare the entire 4 GB space as you can store code, you can store data, you can read write on it, you can store stack, everything, and then finally the operating system will demarcate this area and it will manage it. By this what you lose? You lose entire security that is offered by the Intel architecture. But why did people write such a code? Because they don't want it to be Intel specific, right? They want it to be, they want to quickly port this OS onto a SunSpark or into a ARM or into another architecture. So there has been a constant threat that if the architecture dies, or if the architecture guy becomes hostile to me, what will happen to my software? What will happen to my operating system, right? If it is an open source operating system effort, then I care a damn for the architecture, because if that fellow dies, my entire effort will go off. So I don't want to be specific to that architecture. If I am a closed source architecture, I have a commercial interest in that, right? So I want to make one software which will run on all the architectures that were in the past, currently executing, that may be in the future. So I am looking at things like that, right? So when you get into these type of issues, please note that compilers will not do something which is very, very specific for an architecture, right? We will talk more about this as we proceed in the course, but that I have given this background. Can you tell me an example where one-bit prediction can help? So the simple thing, right? If I have a do-while statement, right? So if I have a for and while statement, then what will happen? All not taken. If I say not taken is default, then the one-bit prediction will work beautifully. 99.9999% it will work correctly, and there will be only one misprediction. But in the case of a do-while statement, what will happen? The first time it will mispredict. First time there will be a mispredict, because it will say not taken, it will this at this stage it will say not taken, but actually it will be taken. Then from the next time onwards this will become taken, it will continue to be taken, and only at the last time again it will say taken, but it will fall down, which is not taken. So there will be 2 mispredictions totally in the case of a do while loop, while in the case of a in a for and while loop there will be 1 misprediction there, correct. So in that context I need not do static, I need not depend upon the compiler to do any optimization for me, still I can basically get things working. So 1-bit predictor assumes a dumb compiler and still can get very good predictions for both for, while and do while. In the case of for and while I will have 1 misprediction, but in the case of do while I will have 2 mispredictions. You are able to follow? So that is why 1-bit prediction becomes interesting. Okay. Now let us go into 2-bit prediction. So what do you mean by 1-bit prediction here? I had 1 bit here, okay, in this, right. Now we will have 2 bits here. So 2-bit prediction essentially means what are the 2 possible bits, values of the 2 possible bits? I have 0 0 0 1 1 0 1 1, 0 0 0 1 1 0 1 1. Okay. Now we will do a state machine for this. Now let us do the state machine for this. So initially I will start, this is not taken. So the prediction here is not taken, the prediction here is also not taken, taken. If I am in not taken 0 0 not taken state, if I again, if actually there is a not taken there, if that branch again it is not taken, I will maintain 0 0. If it is taken from this state, I will go to not taken, again 0 1 not taken. Again if I get not taken, I go back here, but if I get taken, I come here, okay. And here if I get taken, I go here, if I get not taken, I go back here, and as long as I haven't taken, I will be here and not taken. Okay. So what I have written inside the circle is the prediction, what I have written as the labels of the edges is actually what is happening to a particular branch. Okay. Are you able to follow? Right. So this is a 2-bit prediction. Now what happens? Initially I will say not taken. So this is the initial condition. So initially the branch is not taken. So I will predict for this is for every branch, please note that this is for every branch. So say 1005 there is a branch, target address is L1 and initially it is not taken. If that branch is not taken, again it will remain at 0 0. So I will predict not taken first. If the prediction is true, then I will remain at 0 0. But if my prediction becomes false, I will go to the state 0 1. But there also I will predict only not taken. Again if my prediction is wrong, that is it is taken, then I will go to the taken state. Then I will, and again if I get not taken, I will come back to this not taken state. Again if that is taken, I will go to this taken state, right. So this is how. So at least 2 times I have to see not taken so that I decide on not taken, right. But at least 2 times I have to see taken before I decide on taken. In the previous case I just saw once, if it is taken, okay, I agree with him. Now I say let him do twice, then I will agree with him. So can you give me an example where 1-bit prediction becomes stupid but 2-bit prediction becomes better? So can you give me an instance where 1-bit prediction screws up while 2-bit prediction will work? So what happens? Last even example, we had the actual thing was taken, not taken, taken, not taken, taken, not taken. Okay, this is actual. Now what would have happened? We started off with not taken, then it was not taken. Please note that this succeeded. And again it went from taken, so it was 0 0, and since it was taken, this became 0 1, and I predicted not taken. Again I get taken, so I predict not taken. Oh, again I get not taken, I again go back to 0 0, so this is not taken, so this is not taken, so this will go on like this. Okay, so 50% of the time I will succeed. Okay, where 100% failure, so I brought it down by half. So my program will work with respect to branches alone, it will work twice faster. Okay. Can you give me an example where it will fail 100%? Yeah, you should adjust this modulo, no? Instead of modulo 2, if I make modulo 3 or modulo 4, it can kill you. Okay. So now the next thing is I can now go to a 3-bit predictor, which will have 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Initially it will be not taken to start with. So every time I get taken, I go to the next stage. Okay. And every time I take not taken, I go back. And here not taken, I remain here, taken, I remain here. Okay. All these will predict taken, while all these will predict not taken. Okay. Now, so there is one of the papers which basically says that a 2-bit predictor is as good as k-bit predictor. So we need not go to 3-bit, 4-bit and all. Like I can keep on extending. Each one will give me another paper. Okay, no, this. Okay. But then somebody put a stop to this. Somebody got pained. Let us put a stop to this. So 2-bit predictor is best. It is as good or better than k-bit predictor, k greater than 2. Okay. So that was the end of the story. Okay. Now this is dynamic prediction. Okay. Now, but this is dynamic local prediction. Why local? Why that adjective local? It is the decision is made rather than the way the decision is made based on the behavior of that branch. The prediction decision for a branch is made based on the behavior of that branch and not any other branch, right? 1005, how do I predict for 1005? I take the history of how 1005 behaved in the previous instances. The decision for 1005 is not influenced by anybody else. Okay? The decision for 1005 is not influenced by anybody else, or is not influenced by the decision of other branches, and that is why I make this, that is how I make this decision. So that is why we call it as dynamic local prediction, right? Right? So that means in next Monday's class you will have dynamic global prediction, right? So the moment we introduce an adjective, there is something above that adjective. So So what I want you to think out is why there is a necessity for a global prediction. Okay.